speed up. Let's make a few tests. Seconds. Everyone's ready, right? Every team have all your members. Okay. Alright, so if everyone's ready, we will begin the second round. And now the opponent will challenge the reporter.
We would like to challenge from number 12, straight motion.
Sorry, reject.
Challenge is rejected.
Lastly, we would like to challenge problem number 10, droplet explosion.
Number 10.
Is that the challenge?
The challenge is accepted. Number 10. Now the reporter has 5 minutes now to prepare. after you take a stage.
Our number of judges, they use tomatoes on the reporter from our short competition at school. Now I'm going to present problem 10, job explosion. And this is our problem statement. When the drop of the water mixture is passing on the surface of a hydrophobic liquid, the resulting drop is sometimes fragmented into small droplets. Investigate the parameters that affect the fragmentation in the size of the final droplets. And this is our main focus. Although the method radius and diffusion rate of the droplet depends on the parameters and how to estimate the noise concentration to observe this phenomenon. And this is our process we are going to present today. Let's begin with the introduction, next to theory, so its implementation, and then conclusion. Let's come to our introduction part. A drop is composed of water and isopropanol and oil on the surface of oil. And an initial drop is composed of water and alcohol. And we think refer as the amount of droplets gradually begins to fragment and decompose centrifuges of smaller droplets out from its perimeters over time. And in our experiment, the droplet has a uniform composition initially, but after a short time, some alcohol evaporates in the droplet. The depth in the middle is relatively deep, and the surrounding area is shallow. And the evaporation during the area is the same, and the depth of the mixture is different. And therefore, in comparison, even if the same amount of alcohol is evaporated, the ring concentration will decrease more. Then let's set up a subtension gradient, and we call the subtension in the middle and the high subtension at the ring. And the subtension gradient will make the water molecules at the center being pulled by the water molecules at the ring. And the reason for this stability is because the mixture concentration becomes lower than the normal concentration after some alcohol evaporates. And this is our experiment video. We take the double speed. As you can see, after spreading and fragmenting into small pieces, the water will finally stream back. And the reason for expanding first and then retracting is because the alcohol will evaporate and the initial kinetic energy will push the droplet. And this phenomenon we call the Mercurian effect. And the Mercurian effect is the Mercurian effect. It happens whenever there is a subtension on the surface of liquid, and molecules attraction cause the water to be circulating, and that's a principle of this phenomenon. And there are two pictures of before and after adding a mixture. And here we take a more obvious example. You can see that all the papers will gather to the edge, and this is because a drop of solid water in the center will have a lower subtension. And here comes to our theory part. And consider all the facts. This is the formula we can get it. And K is the function to a time. And in other words, it's the time-dependent speed parameters. And we consider all the facts that are proportional to radius. And in the middle term, it's the hydrostatic force, and this is the original one. And because we need to focus on the radius, so we change this formula. And after arranging, we can find out that hydrostatic force can be expressed the K naught multiplied R naught and divided radius Q. And the depth is the static force. And minus means acceleration, and the negative B can be expressed like this according to a Bernoulli's formula. And in this phenomenon, we can find out this formula is associated with the radius. And with the decreasing radius of the droplet over time, you can see that if the force on the negative direction, it will become weaker, and the positive direction will become stronger. That's why the droplet will start exploding in the air. And we define the parameters as is the subtension between oil and air minus subtension between mixture and air, mixture and oil. And subtension can be stored as the potential energy per unit area. So the subtension of the interface of this three solution can be expressed as surface energy. And if the subtension between mixture and air and the mixture and oil is greater than the subtension between oil and air, then the droplet will not expand. But if it expands, then it will spring back. It's because the more of the expansion, the greater the potential energy will be. And this is the formula associated with the oil value and the spreading time. And the H is the height of the oil. If the height gets higher, the spreading time will become shorter and the diffusion rate will increase. And let's come to our experiment part. And this is the we say about this experiment, and this shows how we actually do this experiment. And this is the photo of our experiment. And before the experiment, we need to define some nouns in it. And when we drop a droplet into the surface, into the oil, and we call it an initial droplet. And whether until there are more small droplets on the edge, we call it massive droplet. And after 10 minutes, and we recorded the radius, and it's called final droplet. And this is the density we measure the subtension, and minus the weight of the ring, and dividing the length of the ring, we can get the subtension. And in this experiment, we change three variables. The first one is concentration of the mixture, and the different types and the thickness of oil. And why we choose to change the different types of oil and the thickness of oil? That's because the diffusion rate will slow down. When the diffusion rate slows down, there are more time for alcohol to evaporate, and it will create a substantial gradient. And the reason for why we change the concentration of the mixture, that's because it will also change the evaporation rate, and the substantial gradient will be effective too. This is and this time is associated with the concentration. And we can find that when the concentration is between 10 to 30%, the median radius will change, will not remarkable change. But after 40%, the maximum radius will change a lot, and we can find out the force concentration is 37.5%. And after the lowest concentration, we can find out that the final radius is so small and it's so clear to 0. And this time we change the kinds of oil. Castor oil, so sunflower oil, and winter oil, brown rice oil. And we can find that different kinds of oil begin to climb sharply at different concentration of alcohol. And we guess that's associated with the subtension of oil, and with that we can measure the subtension. And because the castor oil has the highest subtension, and we can find in this chart the castor oil falls sharply first, and the brown rice oil falls sharply second. And we can find that with the higher subtension, we can observe the Marconi effect and the lower concentration. And let's come to our discussion part. And we measure the subtension under different concentration of the mixture. We can calculate S, and we will find the lowest concentration for which S is bigger than 0. Then this time we compare the theoretical value and the experimental value, and we can find out they're a little bit different, and we think that's because of the very tailored stability. And let's come to our conclusion part. In the conceptual understanding, we observe this phenomenon and investigate the Marconi effect. And in our experiment, when we change the concentration of the mixture, we find that it's easier to observe this phenomenon at higher concentration. And when we change the types of oil, we find that we now know that when the surface tension of oil is higher, then we will observe the droplets exploding at a low concentration of isopropanol. And when we check the thickness of oil, we can find that when the oil is thicker, and the diffusion rate will become higher. And this is our reference. Thank you for your kind attention.
Thank you.
Okay, I would like to ask some questions. How much dye do you put in your droplet? How much dye? Can you give a quantitative, like how many percentage of the dye is in the droplet?
We always put one drop of the ink.
Of ink. One drop of ink, how much? How much is one drop? Okay, moving on to the next one. What is the definition of water droplet? Water droplet? Yeah. What is the definition of it? Yeah. You referred in your presentation that you just count the water droplet. What is water droplet? Okay, next one. In page 6, please. How do you predict the diagram? Page 6. How do you predict the shape of this? I think that this is a peculiar shape. Yeah. So how do you ensure that the shape is like that?
Because the drop, when we drop it on the surface,
You observe the height, the depth of the drop.
you can definitely can measure the type of this droplet. You just find this.
Please take page 8. Page 8. Okay, I'll just say it. So in the video, I saw that it does not, the center moves, right? So how do you track it? How do you track the center radius?
We just find it by our eyes and we
See
find
it,
it
it does move. It moves right here.
to set the mass.
Okay, that's it.
Okay, time is up. Your opponent has 3 minutes to defend.
droplet explosion. So this is a problem statement. When a drop of water mixture, for example, water alcohol, is disposed on the surface of a hydrophobic liquid, for example, vegetable oil, the resulting drop may sometimes fragment into smaller droplets. Investigate the parameters that affect the fragmentation and the size of the final droplet. For overview of the report, the phenomena observed that when droplet contracts the hydrophobic surface and it spreads and explodes into smaller droplets. In their theory, they discuss damping cost fluid, fusion rate, surface tension gradient, and Marangoni flow. In their setup, they use different concentrations, different types of oil, for example, rice grain oil, sunflower oil, and the thickness of the oil. In their experiment, they find they discuss about the final droplet size with radius. So let's talk about some pros. They got clear schematic diagrams in deep theory, which they discuss using a lot of mathematical formula, and they got good time management. For cons, there are some contradiction in your theory and your explanation, in your experimental explanation, which is not intuitive and does not truly explain the phenomenon, and lack of error analysis, which in your graph there's no error bars. So there are a lot of points will be discussed later. So the theory we'll talk about how to predict the shape of the water droplet in your theory, and what causes spreading, what causes the fragmentation, drops, and I believe that in your experimental video, the final drop size is not uniform, and we'll discuss about how hydrophobic is the oil, and how does it affect the dissolve of the liquid, whether water mixture and hydrophobic liquid are necessary as the problem stated. Just mention it. And how did you get the characteristic form? How do you get the characteristic formula on page 15? There are some measurement, the error of injecting apparatus, and the radius shrink. The radius shrink does not shrink in the same center. I would like to discuss more about the tracking technique of the radius. For experiment, you did not quantify. You did not quantify the effect of dye, and using a barrette is not a good initial volume control. And there are some ways to ensure that the water mixture of droplet is not a steady stream. And later we'll discuss about the temperature. Okay, I would like to discuss. So first, I would like to return to the shape page, please. I believe that the oil I need to okay. Page 6. Yeah. So how can we ensure that the shape of the droplet will be like this?
Because it comes from our reference, we find that the droplet and the surface can be expressed like this, and the center droplet.
You got real experimental pictures or data that
We can measure it.
you can measure. So how thin do you think the layer is? The height gauge is how thin do you think it is?
I think it's always, it might be just like 0.2 millimeter, and it will always be bigger than the ring.
Have you shined a strong light on the droplet before? Yeah, strong light, not droplet. Okay, so I would like to propose my idea for measuring the deep of the droplet. So you can shine a strong light. The thin film will occur thin film interference. Then you can compare the color with Michael Levy chart, which then you can predict the deep of the droplet at every single time. Okay, let's talk about the cause of the spreading. as mentioned, it is mainly caused by Marangoni effect, right?
Yes.
Is it correct? Okay. But I believe that there are two Marangoni effect, which is caused by concentration difference and temperature. So, but as in your video, you show in your theory, you show that the water molecules pulls upward. How do you explain that? Marangoni effect is basically due to concentration difference, which result in surface tension gradient, right? Is it correct? Okay. So, but you just said that it just developed the surface tension gradient. So I would like to ask, how do you think okay, so I think that the concentration difference, which result in different surface tension. So in the diagram here, the thin part has a higher evaporation rate, causes lower concentration, then develop a higher surface tension in the red part, then it will be cooled off. So I think this is not explained in your theory. So yeah. I would like to talk about the fragmentation. So I think you only explain the spreading, not fragment into smaller final droplets.
Take a picture of the final droplet and with the center.
Yeah. So why will it be pulled out like this?
Because the surface tension is different.
But will it uniformly be pulled out, not fragment into smaller droplets? What is the main cause of smaller fragment into smaller droplets?
Because the droplet into the surface of oil gets fine. Because it has the surface tension gradient.
Yes.
Going effect.
Yes. Yes.
Because the droplet is going.
Okay, so let me use the plastic. So I'm talking about the concept that there exists matter of flow. Yeah. So when it's developed like this, not fragment into smaller droplets. Yeah, it will just expand, not fragment into smaller droplets.
Because of the droplet increase, so natural.
I believe that in the video it kind of developed a shape like this. How do you explain it? And why did this shape end up with smaller droplets break up? Why? Can you explain it? Yes.
We didn't find this phenomenon in our video.
Okay, so I believe this is a phenomenon referred as Rayleigh plateau instability. So when a stream of liquid is developed, there are perturbations. The perturbations will then develop uniformly radius volume, and thus, due to the Galileo-Laplace equation, it says that delta P equals gamma times the curvature. Small radius parts will have bigger pressure, and thus pulls the liquid and thus break up. Okay. So then we'll talk about the droplet size, which is not uniform in your video. And explain why the final size of droplet is not uniform. Yeah, in your video, it's not uniform, right?
As in aspect, when we drop the oil on this thread, and the oil will be not a uniform condition.
So how do you measure the final size of the droplet?
When we drop the droplet, and we take a picture, and we use imagery to measure it.
Okay, so we track every particle. Do you observe high concentration droplet which fragment into smaller droplet that your eyes can't even see? Do you observe this phenomenon?
We didn't observe.
Okay, so moving on. So how do you? I think that hydrophobic is the concept of the extension of. There exists some extension. So like they're less hydrophobic or more hydrophobic. So it then will result in some liquid dissolve, like alcohol dissolve in the oil. Will this dissolve affect your calculations? Okay, so moving on, how do you get your characteristic formula?
We get this formula from different extent.
Reference. Okay, so did you know why we can write down that characteristic formula? Did you know?
Because
There's no, I didn't see any derivations of the formula, so I just like page 17. I just see you pop it up. 17. The character, yeah. I believe this is the characteristic of the radius and the characteristic of time. Did you derive this? How can you derive this formula?
this formula is according to the radius and the time, spreading time.
Yes. So how do you derive it? Like there's a various parameters. Okay, never mind. Moving on to the next question. So I believe that you did not control the volume of initial drop, right? You actually so when you use a device like this, the droplet is not small enough. So when you dispose it on a oil, it will develop a stream. So not saying steady according to this, so maybe like this. But it is continuously contacting the oil, and thus this reddened. So this oil is this mixture is not fully contact with the oil. But the spreading will occur according to your theory, right? Yeah. So if this will end up with drop. So what is the volume of drop? What is the volume of drop? How much is the volume? 2 milliliter. I think that this big of droplet will really develop this kind of phenomenon. I will propose a more nicer volume control which is pipette. 0.2, but this is still too big. I believe that pipette can decrease this size to microliter. Okay. I think the time is up. So I'll start my summarize. So we talk about the prediction shape of the series, and the order to give no explanation of the shape of the model droplet. I think that's it. And what causes the spreading? In this theory, he does not explain why the spreading occurs. And I propose a much nicer explanation, which is the concentration difference cause surface tension gradient, and thus cause Marangoni flow. And next is what caused the fragmentation. I talked about the ring plateau instability, and I didn't get answer of how hydrophobic is the oil, and I don't know why to derive this characteristic formula, and we talk about initial volume of the drug.
how can you assure that every time you conduct your experiments, the concentration of solution is always staying at a constant? Okay, thank you. So this one is for the open. So you have mentioned that temperature might have some effects on this phenomenon.
Yes, I believe that concentration difference is the result of evaporational rate at various deep of the development of the droplet.
Okay, thank you. And for reporter, can you turn to page 26? So we realize that you have a curve in your graph. And can you explain the curve?
This is the curve for the phylogenetics. And we also
Yeah.
take a picture.
And how did you get the curve right here?
Curve. That's because when the concentration is between 10
Yeah,
and 10.
how did you get that? Did you get that from theory or from your experiments?
From this experiment.
Okay, thank you. And then there's a question for both of you. So in the phenomenon demonstration, we realize that droplet in the outside is smaller than the inside. And do you have any explanation to that?
Can you repeat your
Like why is the droplet in the outside of the radius is smaller while inside the droplet?
Okay, so I think that basically in this drop it is like a raindrop, a water drop is a curve, then the air going to flow, pulls it out, and develop a thin film.
How about you? Like why is the final droplet why is there so many different radius of final droplet?
Just like we discussed before. Chocolate in the outside becomes smaller.
Okay, so in your theory, you mentioned that theoretically the lowest concentration of this effect is 40%, right? Why do like how did you get this number? Like how did you get the theoretical lowest concentration?
In our theory,
How did you get that?
we use the subtension, surface tension problem.
Then why is it 37.5 or even 30%?
In our experiment, we use the 35% and 37.
Why does that work? Why does that work?
Time is up. So we give us 2 minutes.
So this is public statement, and the focus is to explain the phenomenon and test out different parameters. So our first summarize what the reporter said in the report. So the phenomenon is that a modern droplet strangely begins to fragment it, and then decomposes, sending fingers of smaller droplets out. And the theory they mentioned is Marangoni effect and surface tension gradient difference. And they've also mentioned Brunner's formula and error caused by radiator instability. So they seem to have no negative elaboration on that. And their parameters have tested out different types of oil, like castor, sunflower, brown rice, and green germ oil. And they have tested out different thickness of oil and the concentration of mixture. So here's the pros and cons of the reporter. So they have clear video demonstration diagram, they have conservative variables. However, they have no lab. They didn't mention the reference of how they get their image and videos, and did not explain what radiator instability is, and did not consider the effect of ink to the surface tension. And this is quite big according to the experiments, as they have mentioned, and did not consider the change of concentration even before they dropped it into alcohol evaporation. And here are the pros and cons of the opponent. So they have on-point questioning and filled in the gap of the report theory, and have proposed valid idea to measure the depth of the droplet with thin film interference. However, they have lacked engagement with the reporter, and they kind of only show their opinions. And they have bad time management. And so here's the discussion between the reporter and the opponent. So the first question the opponent asked is the depth of droplet and how they ensure every droplet is the same. And the thin film, so they proposed the idea that using thin film theory while comparing that with micro-Lorentz charge. And the reporter has given no answer to this. And we agree with the reporter that might be a variation, but we think that the suggestion given by the opponent is very plausible. And this is the second discussion about the cause of spreading. So the opponent asks what is Marangoni effect and why does it cause the spreading of the particle? And the reporter did not give an answer. However, but the opponent given quite a clear explanation to this. And we think that reporters should elaborate on this theory in their report. And the third discussion is on what causes the fragmentation. And the opponent asks about this and why fragments but not expanding as moved back outward. And their answer to that is radiator instability causes it, and I believe that clearly explained this on the board. And we think that reporter should give a more explanation to this. And the fourth question is about the droplet size is not uniform. So the opponent asked how to measure the final size and the small droplet. And the reporter said that estimate the dropping location and track particles with ice. But we think that reporters should maybe put out some of the image that to prove that they have conducted this experiment. And the final discussion is that Marangoni flow pulls out the drop out. And the report is given the answer that they have the droplet is 2 millimeters, and we think that it should elaborate more. So here are some point lists that we would like to point out. So the time expansion that reporters did not mention, and the opponent did not ask about this because they have mentioned that alcohol is constantly evaporating, but they didn't say that how they make sure that it's constant all the time they conduct the experiments. And they did not quantify the hydrophobic gradient. We think they can improve the gradient. Thank you.
This is our remark on the report. Thank you very much.
Thank you. Questions from the reporter?
Yeah. So the final size of the droplets refers to the size of the drop of water initially dropped. Where the tiny droplet fragmented.
Do you understand the question? Do you understand the question?
From our chart, we can find out if the construction of the droplet is 40% or 90%.
Asking which radius were you measured? Are you measuring the radius of the whole block or the radius of
We measure
the
the
radii of the tile?
each part to each part.
So you're measuring the radius of the whole thing.
Yes.
But I thought the question was asking you what the size of the droplet is, the tiniest droplet that this drop fragmented into.
Measure the final droplet. The radius is in the center of this droplet. The center.
Okay, so you didn't measure the size of the droplet.
The picture. The picture is small. I think the question is, so the figure on the right, did you measure the radius of each of the small ones? Okay.
So the answer was no.
Okay. Any questions? Well, I should exercise my right as the chair. This is a question for all of you. Have you ever considered the type of alcohol will make a difference? You use what type of you use isopropyl in your experiment? The type of alcohol. There are many types of alcohol. I know you are too young to drink. Yeah.
Can I answer?
Yes.
Also, I think that different types of alcohol have different evaporation rate, which induce different surface gradient, and thus cause phenomenon change. Yeah.
Okay.
Our experiment also with the alcohol.
Excellent.
You can find out the relation that are different.
Different alcohol types have different density and different evaporation rates. So for this phenomenon, is to see the concentration will be different. The concentration will be different for using different alcohols.
Concentration is parameter you can control.
Yeah. No, I mean like
For the concentration to succeed for this phenomenon to works, it's will be different because due to different alcohols, different characteristics.
Thank you. More questions? Okay. Sorry, I have one more question. Yeah, so the type of alcohol, your assumption is all alcohol evaporate to the air, right? Have you ever considered that alcohol can go into the oil?
I discussed my proposal. So actually, different types of oil will diffuse, will dissolve little alcohol. So I think it is also important rather than control.
Okay.
We agree with the opponent that it might be a possible fact.
Okay. Okay, thank you. Your final chance for questions? No? Okay. Okay. Let's give the jury a little bit time to make up the number. So now let's keep the marks for the report. 7, 7, 7, 6, 6. And now for the opponent. That's 8, 8, 9, 7, 8. Finally, the reviewer. Yes, 7, 8, 8, 7, 7. Okay. Okay, now all the marks are set, and thank you. So let's have 15